Welcome back to the Deep Dive. Today, we are undertaking a deep dive into the hidden mathematics that powers virtually every piece of modern sensing technology.
Mm.
We're talking about the highly sophisticated algorithms that exist purely in software, transforming these raw electromagnetic waves into precise, actionable intelligence.
Yeah, from the military jet tracking targets at Mach speed to the cruise control system that's guiding your car on the highway.
We're really exploring the mathematical brain of modern radar.
That's exactly our mission today. When people think of radar, they often, they visualize the physical dish or the big antenna array,
The hardware.
the hardware. But the real magic, the part that determines whether a system sees a weak target or ignores a strong jammer or handles high-speed clutter, that's all in the computational pipeline.
And the raw signal that comes off that antenna is just chaos, right?
Complete chaos. We're talking gigahertz oscillations polluted by noise. So our task today is to walk you through that entire processing chain from that gigahertz chaos right down to a geometrically precise target location.
And our sources for this deep dive give us a really fascinating blend of foundational theory things like, array physics and complex signal representation, and then the really cutting-edge concepts that make autonomous systems possible today.
Right. Things like space-time adaptive processing, advanced CFAR, and distributed localization. We've broken this analysis into 3 core acts for you. First, we have to understand the signal fundamentals.
How we tame that high-frequency wave.
Exactly, and convert it into a usable digital stream. Second, we move into detection and localization, focusing on how speed and distance are extracted at the same time. And finally, we will explore advanced adaptive processing.
The dynamic battle against interference and clutter.
That's what defines these high-performance systems. Okay, so let's unpack this and start with that foundational barrier, just dealing with the sheer speed of radio frequency signals.
Right.
The initial problem is really one of scale and speed. Modern radar operates using carrier frequencies, what we call FastC, often in the S or X bands.
Which means several gigahertz. We're talking billions of cycles per second.
Billions. So if we adhered strictly to, the Nyquist theorem and tried to process that signal directly, we would have to sample it at tens of billions of times per second.
And that, just intuitively, sounds like an engineering nightmare. Throwing billions of samples per second at a standard digital signal processor just to track a target would require impossibly expensive, power-hungry hardware.
It's just not practical for mobile systems like an aircraft or a car.
Not at all.
It creates a computational wall. So the ingenious solution that engineers developed decades ago is what we call the complex baseband representation. It's the core of IQ processing.
Okay, so what's the goal here?
The goal is to shift that massive high-frequency signal spectrum down to DC, down to zero frequency, which we call baseband, without losing any of the embedded information.
So we're taking the useful information that's kind of riding on this impossibly fast carrier wave. We strip the carrier away, and we're left with just the payload behind.
Exactly that. The mathematics describes the baseband signal as SAT plus JDUP QT. This complex representation, where J is the imaginary unit, contains 2 components.
I for in-phase and Q for quadrature.
Correct. And now that the signal frequency is centered at 0, the required sampling rate is drastically reduced. We're now sampling in the low megahertz range, which, standard, inexpensive digital signal processors can handle easily.
I really like the radio station analogy here. If the gigahertz carrier wave is the massive broadcast tower, the IQ processing is like stripping away all the enormous RF hardware needed just to carry the signal.
Right.
And focusing only on the audio information, the music, and the voice, which you can then, process easily on your laptop.
That is a perfect way to visualize the efficiency gain. And the key mechanism for achieving this clean separation is quadrature, the critical 90-degree phase shift. Physically, the incoming RF signal is mixed, which is just a multiplication by 2 separate local oscillator signals. One is a cosine wave, that's the I path, and one is a sine wave, the Q path, which is offset by 90 degrees.
And that 90-degree separation is, you're saying, non-negotiable.
It is absolutely fundamental.
Why is that orthogonality, that 90-degree phase difference, so important?
Because it ensures mathematical independence between the 2 channels. Cosine and sine waves are what we call orthogonal functions. When you integrate their product over time, the result is 0.
Meaning there's no crosstalk.
Precisely. The I channel does not bleed into the Q channel and vice versa. And this separation is crucial. Think about digital communications, modulation schemes like QAM.
Quadrature amplitude modulation.
Right. They transmit multiple bits per symbol by mapping them to unique combinations of I and Q values. If that separation fails, your symbols just blur together and you get immediate data loss.
But of course, we're moving into the real world now, where this process is handled by analog hardware, mixers, local oscillators, amplifiers. Nothing is ever truly 90 degrees perfect.
No, it's not.
And the sources warn us about this inevitable hidden flaw: IQ imbalance.
Yes, the difference between the mathematical blueprint and the physical reality is where performance just crashes. IQ imbalance describes any deviation from the ideal I and Q channels.
And there are physical sources for this.
There are three we are constantly fighting. First, gain mismatch. The amplifiers in the I and Q paths might have slightly different gains, so one channel is stronger than the other.
Okay, and second.
Phase mismatch. The local oscillator might generate a 92-degree or an 88-degree phase shift instead of a perfect 90.
And both of those issues, they distort the symbol shape, right?
Yeah.
If you map a digital symbol to a perfect square on this IQ plane, any mismatch will turn it into, what, an ellipse?
Exactly. The tight cluster of constellation points spreads out, which reduces your margin against thermal noise. And this isn't just theoretical. Our sources are brutally specific on this. They state that a mere 3 to 5% amplitude mismatch, or just a few degrees of phase error, can result in a crippling 1 to 5 dB degradation in your signal-to-noise ratio.
Wow.
That is the difference between reliably tracking a target and missing it entirely, purely due to some analog component drifting over time.
It's genuinely mind-boggling how sensitive these systems are. A 5% error in a component gain can essentially slash your radar's effective range by a quarter.
It's huge.
That level of precision feels almost impossible to maintain over temperature changes or, component aging.
And that leads us to the third critical flaw, DC offset. This is often caused by asymmetric biasing in the analog mixers. When this happens, a very strong, steady signal is introduced right at f = 0 in the baseband spectrum.
That sounds nasty, because if your signal is supposed to be centered around 0, a huge spike there must just overwhelm everything else.
It does. That DC offset spike is extremely disruptive. It can actually saturate the receiver's automatic gain control, or AGC, circuitry.
So the AGC thinks this massive spike is a real signal.
Right. It thinks it's something it needs to accommodate, so it radically reduces the overall system gain. This action effectively deafens the receiver to all the genuinely weak, distant echoes we are actually trying to detect.
So if this imperfection is born in the analog world, how do we use digital processing to fix it after it's been digitized? Do we have to, shut down and recalibrate the hardware constantly?
No, thankfully we rely on adaptive digital fixes. Instead of relying on static calibration, high-performance systems use continuous tracking algorithms.
Okay, what are those?
We can use methods like the least mean squares, LMS, or the more complex recursive least squares, RLS algorithm. These algorithms observe the incoming IQ data stream and constantly calculate a compensation matrix. We'll call it C in the digital domain.
And then this matrix is estimating the errors.
It's estimating the current gain and phase errors, and it applies precise, instantaneous digital corrections to realign the I and Q channels back to perfect orthogonality.
So it sounds like a continuous self-healing system.
It is, and for extremely high-speed data links, such as those using, say, high-density modulation like PM4, the system requires even more specialization.
Right.
The sources highlight the use of digital feedback equalizers to not only correct the IQ imbalance, but also to compensate for channel impairments, and that DC offset all at the same time. This ensures maximum signal integrity, which is, essential when your data rates are pushing close to the Shannon limit.
So we've mastered the signal in the time and frequency domains. Now we have to introduce the third dimension, space.
Right.
This is where we transition from single antenna processing to sophisticated array processing, whether that's a massive ground radar or a small phased array embedded in a mobile device.
We move from time domain complexity to geometric complexity, and this is all centered around the concept of the array manifold.
Okay, what is that?
Let's conceptualize a uniform linear array, or ULA. It's just a straight line of m elements, typically spaced at d = lambda over 2, or half a wavelength.
So the array manifold is the mathematical representation of how a signal's direction of arrival, theta, translates into a unique set of phase shifts across all of those m elements.
You've got it. So if the signal arrives from directly ahead, 0 degrees, there's no phase difference across the elements because the wavefront hits them all at the same time.
But if it arrives at, say, 45 degrees, the wave hits the elements sequentially. creating this predictable phase progression that increases with each successive element.
You've captured the physics perfectly. The steering vector, which we denote as a theta, is the mathematical notation that captures this unique phase relationship. The phase shift for each element depends on its index, the spacing, and the angle.
And you mentioned that standard spacing,
Yeah.
d equals lambda over 2. Why is that specific spacing so critical? I mean, if we space them further apart, we'd need fewer antennas to cover the same physical area, wouldn't we?
We would, but at a catastrophic cost: spatial aliasing.
Hmm.
If the spacing is too large, signals arriving from drastically different distinct angles might impose phase differences that look identical to the processing unit. This ambiguity means we can't tell if the target is at plus 30 degrees or minus 150 degrees.
So that half-wavelength spacing is the spatial equivalent of the Nyquist-Shannon theorem.
That's a great connection. It ensures we sample the phase progression often enough to reconstruct the true angle without any distortion. It ensures phase uniqueness across the entire visible angle range, typically plus or minus 90 degrees.
So once we have this mathematical map, how do we actually use it to focus the array's sensitivity in one direction, the process we call beamforming?
Beamforming is the practical application of that steering vector. Our goal is to electronically steer the array to a specific target angle, let's say theta 0. We do this by calculating a weight vector, W, which is a conjugate of the steering vector for that angle.
Okay, walk us through the physical meaning of applying that conjugate weight. What does that actually do?
So the original steering vector, a theta 0, told us the precise propagation delays, the phase shifts that the incoming wavefront incurred as it traveled across the array.
Right.
By applying the conjugate of that vector as a weight, we are precisely undoing those delays. This causes all the energy received from that one direction, theta 0, to align perfectly in phase when it's all summed together.
Which is constructive interference.
Exactly. The energy from the target direction is amplified dramatically.
And what about energy arriving from every other direction?
It experiences destructive interference. Signals arriving from any other angle will have phase shifts that do not align with our applied weight vector. So the signals will cancel each other out, and the result is the formation of a spatial filter, a beam, that only listens in that one specific direction.
And this works because signals from different directions have nearly orthogonal projections on the array manifold.
That's the mathematical basis for their separation. This is a foundational concept. Array processing is fundamentally about applying the right phase shifts to maximize constructive interference at the output.
With the signal spatially filtered, we can now turn to the critical task of measuring the target's distance, its range, and its speed, its Doppler.
And this is achieved through the construction of the range Doppler map, RDM, which is really the central output of any pulsed radar system.
The RDM gives us distance and speed simultaneously. How does the radar manage to extract two pieces of information from a single reflected pulse sequence?
It's a sophisticated two-dimensional matched filter process that separates the information into what we call fast time and slow time.
Okay.
Step 1 is range compression using fast time. This occurs within a single transmitted pulse. Modern radar rarely transmits a single, simple short pulse. Instead, we use sophisticated waveforms, most commonly the linear frequency modulated LFM chirp.
That's the signal that sweeps linearly in frequency over the duration of the pulse, right? Why is that chirp so necessary?
We use the chirp because we want two conflicting things at the same time. We want a long pulse duration to maximize the total energy we transmit, which improves detection range.
But you also need a very short, sharp pulse peak to get high resolution.
Exactly. The chirp solves this. When the received echo is processed using a matched filter, which is a correlation with the inverse of the transmitted chirp, all the energy that was spread across that long pulse duration gets compressed into one incredibly narrow, sharp peak in time.
So the range resolution, which we call delta R, is determined entirely by the bandwidth of that chirp.
Precisely. Range resolution is determined by C divided by 2B, where B is the chirp bandwidth. And this is a crucial trade-off. If you invest in a wide bandwidth, let's say 100 megahertz, your range resolution is excellent. You get about 1.5 meters.
But if you only use 1 megahertz of bandwidth,
Then your resolution drops to 150 meters. So range compression is step 1, and it gives us all our range bins.
okay, so step 2 is extracting velocity, or Doppler compression, which you said happens over slow time.
Correct. This is where we look across multiple pulses, defined by the coherent processing interval, or CPI, which consists of, say, L pulses.
So a moving target imposes a tiny, predictable phase shift on the echo from one pulse to the next.
Exactly. By collecting all L pulses and performing a discrete Fourier transform, usually a fast FFT, we effectively separate those distinct phase shifts into velocity bins, giving us the target's Doppler shift.
And this FFT across the pulse train is what gives the system its immense detection power, the coherent processing gain.
Yes, the coherent processing gain, CPG, is the key benefit of integration. The SNR improves by 10 log base 10 of L in decibels. So if you use, say, 32 pulses, you gain over 15 dBs of signal power.
Which lets you detect targets that would otherwise be just completely lost in the noise.
Absolutely. The RDM then becomes this 2D map. Bright spots are targets at a unique range and velocity. It also clearly identifies clutter. Stationary objects like mountains or ground echoes appear as a strong vertical line running right through the zero Doppler axis.
This all sounds ideal, but the longer the CPI needed for good Doppler resolution, the more we expose ourselves to a kinetic flaw, range migration or range walk.
And this is a major hurdle for high-speed tracking. Range walk occurs when the target's radial distance changes significantly across the L pulses that make up the CPI.
Can you give us an example?
Let's use a concrete one. If your target is moving at a relative radial velocity of 50 meters per second and your CPI lasts 0.128 seconds, say 128 pulses, the target physically moves 6.4 meters during that integration time.
And if our range resolution is only 1.5 meters, that target has just jumped across 4 distinct range bins in that time. I assume that spreading just ruins the coherent integration you just built up.
It absolutely does. Instead of the energy accumulating into one shot peak in the RDM, it spreads across multiple range bins and consequently across multiple Doppler bins.
Which reduces the gain.
It drastically reduces the effective coherent gain. In our sources, this artifact was shown to cause an SNR loss of around 1.07 dB for a 128 pulse scenario. That 1 dB might sound small, but when you are tracking a weak, stealthy target, that loss is intolerable.
So we need compensation strategies. The simple fix must be to just estimate the speed and shift the data back.
Yeah. That's the simplest fix, yes. It's called Doppler-based correction. If we have a rough estimate of the radial velocity, we can calculate the exact phase change associated with that motion for every pulse. We then apply a precise phase adjustment to the raw data of the pulses to digitally align all the echoes back to a common range reference before the final Doppler FFT.
But that simple phase adjustment only works if the target is moving at a constant velocity. I imagine it might struggle with higher order motion like acceleration or extremely fast targets.
That's where we move to the advanced solution, the keystone transform. This is a far more robust geometric correction. When range migration happens, the range Doppler map actually skews. For a target at a specific range R0, the signal might align perfectly, but for a target at R1, it doesn't.
So the keystone transform mathematically warps the data in the time-frequency domain to fix this. How does it achieve that warping?
Conceptually, imagine the range Doppler plane as a sheet of elastic material. Range walk causes the tracks of high-velocity targets to slope across the range bins. The keystone transform applies a frequency-dependent time-sampling adjustment, a kind of frequency warping that makes the slope of all target tracks, regardless of their range, horizontal again.
So it's not just a simple phase shift, it's a structural transformation of the entire data set.
Right. It maps the range-varying data onto a constant range space.
And by getting rid of that range-dependent slope, all the energy aligns perfectly within one range bin before you apply the final Doppler FFT.
Which restores the maximum coherent gain, even for targets exhibiting severe range walk. It truly is necessary for tracking high G maneuvers or, hypersonic targets.
So we've achieved range and velocity detection, but now we face the overwhelming reality of the environment. Our targets are almost always masked by clutter.
Yes. This is unwanted returns from the ground, sea waves, or heavy rain. Critically, clutter can be 100 to 1,000 times stronger than the weakest target we're trying to detect.
That power disparity is massive. If the radar system can't overcome that, the display is just a massive white blob of noise, and the target is completely invisible. You need an intense clutter rejection ratio, CRR.
We do. Typically, 30 to 60 dB of CRR is mandatory. Fortunately, clutter is not random noise. It's predictable.
How so?
It's spatially concentrated, and its motion is slow, usually centered right at the zero Doppler axis. Because of the structure, we can engineer filters to surgically remove it.
What are the main ways we start tackling this?
The initial and simplest method is Doppler filtering, just using a high-pass filter to reject everything near zero Doppler. This is effective, but it has a massive limitation.
Just what?
Any target that is stationary relative to the radar is also filtered out. For instance, an air traffic control radar would lose hovercraft or low-speed helicopters?
So for systems that need to retain that stationary target data, or when the clutter environment is complex and non-uniform, we have to move to adaptive filtering.
Exactly. We shift from fixed filters to algorithms that actually learn the clutter environment. Methods like normalized least mean squares, NLMS, or principal component analysis, work by defining the clutter's subspace.
How does that work?
We feed the algorithm training data time periods where we know only clutter is present, and the system calculates the optimal weights to predict and then subtract that clutter signature from the incoming signal in real time. Our sources show the dramatic effect of this. Adaptive methods can yield an 8.31 dB CRR improvement over simple filtering.
Now let's talk about active interference jamming. If we are using standard beamforming, where we apply a fixed weight vector to steer the beam, a strong jammer placed at a different angle will instantly override the target signal.
Absolutely. The system needs to react, which demands adaptive beamforming.
Right. When a jammer appears, we need the array to instantly and dynamically place a spatial null, a point of zero sensitivity, precisely in the jammer's direction, while critically maintaining full gain toward the target.
And the optimal mathematical solution for this is the minimum variance distortionless response, MVDR beamformer.
You use the word optimal. What makes MVDR the mathematically perfect solution for this scenario?
It's the optimal Wiener filter. It solves a specific constrained optimization problem. Minimize the total power output of the antenna array, that's the minimum variance part, while simultaneously imposing the distortionless response constraint.
Which forces the gain to be one in the target's direction.
Exactly. Unity gain in the known target direction. The optimal weight vector requires the inversion of R, the covariance matrix of the incoming interference and noise.
So by forcing the system to minimize everything except what's coming from the target direction, the math naturally identifies and suppresses the strongest noise sources. It places these deep nulls right there.
The example you mentioned earlier, achieving 51.11 dB of jammer suppression against a 50 dB jammer, shows incredible efficacy. It proves the nulling capability is robust and effective.
But we have to address the cost. The MVDR solution requires inverting that large covariance matrix, which is computationally intensive. If the environment is changing rapidly, calculating that full inversion every millisecond is often too slow.
This is where we run into that essential engineering trade-off. If MVDR is so slow and resource-intensive, what are the real-world compromises engineers have to make? Do we sacrifice some performance for speed?
I assume we have to.
We often do. And that leads us back to the adaptive training methods we discussed earlier, applied now to the spatial domain, LMS and RLS. These methods iteratively update the weights without ever calculating the full matrix inversion. They are fast approximations of the optimal solution.
Okay, let's detail that crucial trade-off.
LMS, least means squares, is simplicity and speed itself. Its computational complexity is very low. It scales linearly with the number of array elements, ABM. It's stable, it's simple to implement in hardware.
Right.
But it is slow to converge. If the jammer rapidly changes frequency or direction, LMS might take hundreds or thousands of iterations to catch up, during which time the target remains masked.
And RLS, recursive least squares, flips that trade-off completely.
Completely. RLS converges extremely fast, often within tens of iterations, making it ideal for rapidly changing environments. It's mathematically much closer to the true MVDR solution at every step. But its complexity scales with the square of the array elements, O of m squared.
And it has other issues.
It does. RLS involves tracking a running inverse matrix, which can accumulate numerical errors over time, leading to instability or even divergence if you're not careful.
So if I'm building a high-stakes military radar where one missed target is catastrophic, I might choose the slightly slower but numerically stable LMS algorithm or even a full periodic MVDR calculation.
Right.
I'm prioritizing stability over raw speed.
That's the core engineering decision. You choose based on the dynamics of the threat and what level of risk is acceptable.
Once we've cleaned the signal, nulled the jammer, and canceled the clutter, we need to make the final declaration. Target detected. This final stage is governed by constant false alarm rate, CFAR processing. Why is using CFAR mandatory? Why can't we just set a fixed power threshold?
Because the noise floor, sigma squared, and the remaining clutter residue constantly change across the range Doppler map. If we set a threshold based on a quiet environment, the system will scream false alarm constantly when scanning over, say, a dense city.
And if we set it high enough to ignore the city, We'll miss a weak aircraft over the ocean.
Exactly. CFAR is mandatory because it maintains a mathematically constant, acceptable probability of making a mistake. The PFA, which is typically set incredibly low, like 10 to the minus 6 or 10 to the minus 8.
So it's not fixing the power level, it's fixing the probability of error. How does the algorithm adapt that threshold dynamically across the map?
It uses a statistical mechanism, the sliding window. When examining a specific cell under test, or CUT, in the RDM, the algorithm analyzes a ring of adjacent cells, the reference cells.
And it averages their power to estimate the local noise and clutter.
It estimates the local power, what we call sigma hat squared. The threshold, eta, is then scaled by this local estimate. The system declares a detection only if the CUT power exceeds this adaptive threshold.
And I imagine different environments require different strategies for how that average is calculated. What happens when the environment isn't uniform?
That's where the different CFR types come in, each designed to mitigate an edge case. CACFR, cell averaging, is the simplest and best for homogeneous uniform clutter, where the noise floor is flat.
Right.
But if targets cluster, the target's own energy can leak into the reference cells, artificially raising the threshold and causing nearby weaker targets to be masked. This is the target masking effect.
So if a fighter jet is escorting another fighter jet, the second jet might be missed entirely because the first one raised the threshold too high for it.
Exactly. To defeat target masking, we use OSCFR, Ordered Statistic CFR. Instead of averaging all the reference cells, OSCFR sorts them by power and selects the Kate value, often the median.
So taking the median means the one big target doesn't skew the whole estimate.
Exactly. It keeps the threshold honest.
And what about the opposite problem, moving from heavy clutter to silence, like an aircraft flying off a coastline?
That's the clutter edge problem, where the noise level abruptly drops. If the reference window crosses that edge, the high clutter on one side can dominate the average, causing a massive spike in the threshold right on the clean side of the edge.
Which can lead to ghost detections.
Or just high false alarms. For this, we use CFAR, smallest of CFR, which divides the reference cells into two halves and takes the smallest estimated noise power from those two halves. This prevents the high-power region from generating false detections in the low-power region.
We've addressed spatial adaptation and temporal adaptation separately. But what happens when the clutter itself is moving, not stationary?
This requires the pinnacle of integrated filtering, space-time adaptive processing, SDAP.
And this usually applies to air-booked radar, where the radar platform is moving and it's looking down at the ground. That motion makes the ground clutter appear to have a non-zero velocity.
Precisely. If an aircraft flies at 500 knots, the ground below appears to be moving toward the radar at 500 knots. This moving ground clutter not only arrives from a specific angle, it has spatial structure, but it also has a specific Doppler shift, a temporal structure.
So if we only apply a simple Doppler filter, we wipe out real targets that happen to have the same velocity component as that moving clutter.
You do. SDP solves this by jointly optimizing the filter in both the angle and Doppler dimensions at the same time.
So SDP combines the data from M antennas and L pulses into one massive processing block. What does that merged data look like mathematically?
We create the SDP snapshot vector. If we have M antennas and L pulses, we stack all that data into a single vector of dimension ML by 1. For example, an advanced system might use 8 antennas and 16 pulses, creating a vector of 128 elements.
Okay.
The target signal is then defined by the space-time steering vector, which is the mathematical combination, the Kronecker product of the spatial steering vector and the temporal steering vector.
So the SIST filter is now aware of both the angle and the speed of every component of the incoming wave simultaneously.
That joint awareness is the source of SISTP's immense power. By processing this combined ML dimensional space-time snapshot, the filter gains ML total degrees of freedom, or DOF.
So in our 8x16 example, we get 128 degrees of freedom.
Right. One DOF is used to maintain gain on the target, which leaves 127 degrees of freedom dedicated purely to nulling interference and clutter.
That's a monumental amount of control. It allows the filter to create these precise, customized nulls in the 2D angle Doppler space, effectively digging the target out from under that moving clutter ridge.
Exactly. The result is a maximization of the signal-to-interference plus noise ratio, or SINR. Step performance is unparalleled, often achieving SINR improvements ranging from 40 to 70 dBs over conventional methods. It's the gold standard for moving platform surveillance.
But once again, we encounter the complexity hurdle. If the full step covariance matrix is 128 by 128, the optimal solution requires inverting that matrix. We established that the full dimensional complexity scales as O of ML cubed. It does.
If ML is 128, then 128 cubed is over 2 million operations just for one matrix inversion. That must make real-time STEP practically impossible for large arrays.
For a full dimensional brute force inversion, you are absolutely right.
Right.
It would take seconds, not the milliseconds required for real-time tracking. This is the biggest challenge in high DOF array processing.
So how do engineers overcome this?
They overcome it by exploiting the mathematical structure of the platter itself. There are two main strategies. First, we use the Kronecker factored structure. We assume that the covariance matrix can be separated into a spatial part and a temporal part.
And this factorization lets you solve the problem by inverting two smaller matrices instead of the one big one.
Right, an m by m and an l by l. This reduces the complexity dramatically to O of m cubed plus l cubed.
That's a massive win. For our 8 by 16 array, we are dealing with 8 cubed plus 16 cubed, which is tiny compared to 128 cubed. Yes, this complexity reduction is what made STEP feasible initially, but even that can be too much for extremely large arrays, or it fails if the clutter doesn't strictly adhere to that factored model.
So there's another strategy.
The second and more robust strategy is reduced rank STEP. We observed that moving clutter, even though it lives in this high-dimensional ML space, often only occupies a very small, low-dimensional subspace within that data.
So we don't need all 128 degrees of freedom to suppress it.
Exactly. Algorithms like joint domain localized STEP or techniques using eigenvalue decomposition identify this low-rank clutter subspace and only dedicate a small, focused number of degrees of freedom, say 8 or 10, regardless of the array size to filtering.
So instead of throwing 128 DOF at the problem, we use the math to identify the core 10 dimensions where the clutter actually exists, and we only process those 10. We sacrifice the theoretical optimality of the full filter for massive gains in speed and feasibility.
And that is the ultimate example of the complexity versus performance trade-off in modern signal processing. We use those faster, reduced rank techniques coupled with parallel processing on hardware like GPUs to ensure the powerful StatPap algorithm can be used for real-time tracking.
So far, our highly optimized system has given us range and radial velocity, and we have a direction estimate limited by the array size. But if we need extremely high precision in 2D or 3D position, especially for covert tracking or complex urban environments, we have to look beyond a single radar.
We do. We need to solve the localization gap using distributed sensing, which brings us to time difference of arrival, or TDOA.
TDOA is fundamentally a geometric technique that relies on precise timing. It requires at least 3, but usually 4, geographically separated receivers, all listening passively to the same target-submitted signal.
Whether that's a reflected radar pulse or even a jamming signal.
And the core principle, as our sources highlight, is hyperbolic geometry. Walk us through how a difference in time translates into a hyperbola.
Imagine two receivers, RX1 and RX2. The signal arrives at them at slightly different times, creating a time difference, delta t. Because radio waves travel at the speed of light, this defines a constant range difference. C times delta t equals d2 minus d1.
And the mathematical definition of a hyperbola is the locus of all points, where the difference in distance to two fixed points, the foci, is constant.
Precisely. The two receiver positions are the foci. Therefore, the target must lie somewhere on the hyperbola defined by that constant range difference.
But a single hyperbola only gives you a line of position, so you need a third receiver.
You do. A third receiver, RX3, creates a second pair, say RS1 and RX3, which defines a second hyperbola. The intersection of those two hyperbolas provides a unique, highly accurate position estimate in 2D space. A fourth receiver is often added for 3D localization and to provide some redundancy.
This sounds incredibly complicated to solve in real time. We're dealing with the intersection of nonlinear equations. Do we rely on slow, iterative numerical methods?
Thankfully, no. The standard method used globally is Chan's algorithm. It's prized precisely because it is a closed-form, non-iterative solution, often implemented using weighted least squares.
Meaning it calculates the position directly in 2 linear steps without the risk of convergence failure or the slowness of iteration.
Exactly. This reliability makes it the algorithm of choice for many modern surveillance and rescue systems.
Now for the Achilles heel, the practical constraints. The entire system relies on measuring minuscule differences in time. What is the biggest risk?
Synchronization. This is the hypercritical constraint. TDOA's accuracy is directly proportional to clock stability. Since the speed of light is so high, a tiny error in time translates to a huge error in distance. Our sources specify that just a 1 nanosecond clock offset between two receivers translates to an unacceptable position error of approximately 30 centimeters.
It's genuinely mind-boggling that 1 billionth of a second in timing error can throw your target position off by a foot. That level of required precision feels almost impossible to maintain across distributed receivers.
It demands specialized hardware. TDA systems must rely on extremely precise synchronization methods, usually employing GPS-disciplined clocks. These use the atomic clock signals from GPS satellites to keep every receiver synchronized down to the sub-nanosecond level.
And even that isn't always enough.
Even then, dedicated computational resources must often be used to estimate and correct any residual clock offsets in real time because temperature fluctuations or cable lengths can still introduce tiny differences.
And what about the geometry of the setup itself? Does the placement of the receivers matter?
Immensely. Accuracy is limited by the geometric dilution of precision, GDOP. GDOP quantifies how the receiver geometry impacts the error. If your receivers are spread out evenly around the target area, creating wide intersecting angles for your hyperbolas, your GDOP is low, close to 1, and your position accuracy is excellent.
But if all your receivers are placed along a straight line,
Then the hyperbolas are nearly parallel, creating a huge uncertainty region. A high GDOP means the system is geometrically ill-conditioned. For precise tracking, like the example GDOP of 1.0027 cited in our sources, you need excellent geometry.
this brings us back to the ultimate synergy, fusion potential. We started with a radar that gave us precise range and radial velocity, which is fantastic for tracking motion. Now we add a TDOA network that gives us precise 2D or 3D absolute position.
Combining those two data streams must create an incredibly robust, comprehensive tracking picture. It creates a fully integrated picture. The radar provides the high-fidelity kinematics, and the TDOA system pins the target to the map with sub-meter accuracy.
We've traced a remarkable complex path today. We began by taming chaotic RF signals, transforming them into manageable digital IQ data by leveraging that non-negotiable principle of 90-degree orthogonality.
And then used adaptive digital filters like LMS and RLS to compensate for the extreme sensitivity of analog hardware flaws like IQ imbalance.
We moved into spatial processing, defining the array manifold to understand direction, and then created the range Doppler map, maximizing detection power through coherent processing gain.
Which is the result of using FFTs across the pulse train. And we had to battle range migration using advanced geometric fixes like the keystone transform to maintain that gain against high-velocity targets.
And finally, we deployed the heavy mathematical artillery against interference. We used MVDR to dynamically place nulls against strong jammers, navigated the critical trade-offs between LMS stability and RLS speed.
And integrated the ultimate solution, SD8, to jointly null clutter in the 2D angle Doppler space, relying on tricks like Kronecker factoring and reduced rank processing to make that massive O of ML-cubed complexity computationally feasible in the real world.
If we connect this to the bigger picture, it all resolves into a crucial engineering decision tree, as outlined in the source material.
Right. If you need high range resolution, the fundamental choice is wide bandwidth, often through an LFM chirp. If you need robust clutter rejection in a moving platform environment, you must move away from simple high-pass Doppler filters and rely on SetAP.
And the core theme across every single stage, from IQ correction to jammer suppression, is that adaptive processing, these OM or OM squared solutions, invariably outperforms fixed, pre-calibrated solutions in the noisy, time-varying environment of the real world.
It does.
This raises an important question, though, as we look to the next generation of these systems. Since modern radar relies entirely on these specific, elegant, deterministic mathematical frameworks, the careful inversion of covariance matrices, the statistically derived CFR thresholds, what happens when we replace this fixed, prescribed logic with autonomous, data-driven machine learning approaches?
Well, here's where it gets really interesting.
I thought so.
That transition is already happening, and it's defining the future field of cognitive radar. Instead of using a fixed mathematical model, we use neural networks trained on massive data sets of environmental clutter. For example, instead of calculating that explicit scaling factor for a CFR threshold based on some statistical assumption about Gaussian noise,
A deep learning algorithm could just learn the optimal decision boundary.
it could learn it based on millions of unlabeled clutter snapshots. It wouldn't be using a predetermined formula. It would be using experience to make the most robust detection decision.
So it's more than just a better filter.
Oh, it goes much further. In a cognitive radar, the system dynamically assesses the environment. Is there heavy rain? Is there a jamming signal? And then autonomously decides which waveform to transmit, how wide the chirp bandwidth should be, and how long the coherent processing interval should last.
So it's adapting its resource allocation and filtering strategy in real time.
It's a shift from applying a known algorithm to intelligently selecting the optimal algorithm or even creating a new one, moment by moment. That represents the ultimate challenge awaiting the next generation of engineers, moving from explicit physics modeling to data-driven autonomy.
A truly incredible deep dive into the hidden world of signal processing.
Sure.
Thank you for guiding us through the mathematics that powers our modern sensors.
Always a pleasure.
And thank you for joining us on the deep dive. We'll see you next time.